Hello there. We are into the third installment of the atomic and molecular spectra series, and we start off. We start this off with the comparison of hydrogen and helium spectra. So we have a comparison to start with. Comparison of hydrogen and helium spectra. Helium He plus, helium ionized helium. Now, it was Pickering in the year 1897 when he discovered a new series of Xi Puppis star. While he was studying this star, he he discovered the series which was attributed first attributed by Rydberg to some form of hydrogen, because its formula that he obtained was similar to that of the Balmer series, Balmer's formula for hydrogen. Later on, some experimental work by Evans, Fowler, and Paschen, it showed that the series arises due to ionized helium. And by putting the formula for, or the atomic number for helium in this, we have the Rydberg, and we use the Rydberg's constant for helium from Bohr's formula. What we get is the wave number. In this case would be simply the reciprocal of the wavelength, which is equal to 4 times, because 4 is the number of nucleons in it. 4 times the Rydberg's constant multiplied Rydberg's constant for helium, and we have the n1 square minus the n2 square. Uh, these values, however, n1 and n2, they are the series. They arise due to the dropping of electron from some initial higher state to a final ground state, or the lower state. And this was, so as to speak, was obtained for n1 being equal to, in each case, n1 here in the first case supposedly is taken as 4, and we have n2 to be equal to 5, 6, and 7, the higher states, and this is known as the Pickering series. Then we had n1 to be equal to 3, and n2 to be equal to 4, 5, and 6, and this is the Fowler series, named after the scientists who obtained them. And then we have n1 to be equal to 2, n2 to be equal to 3, 4, and 5, and then finally n1 having 1, and n2 being 2, 3, and 4, and so on. This was the Lyman series. Now, with these series available, we draw a comparison with the Balmer series for hydrogen. Remember, these are all for helium, and we take the Balmer series where we use the Rydberg's constant for hydrogen, and we have the wave number, which is equal to the reciprocal of the wavelength, and that goes from 1 by 2 squared, which is that for Balmer series, and we get n square over here n are the higher states, that is 3, 4, and 5, and so on. Then for Pickering, if we are comparing this, we have nu bar simply to be equal to, as I wrote it over there, are for helium, Rydberg's constant, and we have 1 by 4 square. The first one, 1 by 4 square minus 1 by n square, where n is here 5, 6, and 7, and so on, which is this thing that I wrote over here. Just rewrote it down there. And in this case, what we are obtaining is, well, the lines, especially for n is equal to 6, 8, 10, these alternate lines, they are expected to coincide with, let me give this n dash for this n dash over here, n dash squared, and let this be n. So this must coincide for n is equal to 3, 4, 5, and so on. But that is not the case. This would have been possible, this coinciding of these things would have been possible in case R of the helium would have been equal to the R of hydrogen, that is Rydberg's constant in each case. In case, that is. But that's not the case at all. There is a difference, and that difference, obviously, when the lines were observed, uh, they were slightly uh, differing. So this is the H alpha, and they would have been exactly placed coinciding with one another, but they were slightly differing from one another. And then these are the in between lines that won't have coincided over there. But certainly the H alpha, H beta, these are the odd numbers for n is equal to 5, 7, and all of that. But we were expecting uh, the lines like 6, 8, and 10 for those transitions. They would have coincided. Obviously, the intensity goes on decreasing, so this these lines would be smaller gradually, and these things would have reduced. And this is supposedly H delta. Now, likewise, this would have these two lines, the difference that you see over here, that shouldn't have been there. They must have coincided, but that's not the case, because the small displacement obviously occurs because there is small difference in the values of RH and RHE, which is again taking us back to the finite mass consideration of the nucleus. So the finite mass of the nucleus does play a role in giving us these kind of results, and they hold good uh, with all these experimental values that were obtained. Now we move over to another part of this discussion, or rather another part which we'll be using to determine a few things, which is the Wilson-Sommerfeld quantization rules. Now, Planck, he introduced the quantum theory by quantizing the energy of atomic oscillators. He said that Planck said that E is equal to n times of h nu, where nu is the frequency of the oscillator and h is the Planck's constant, and n is the integral multiple. Bohr, on the other hand, he quantized the orbits and the angular momentum, and the, considering the circular orbit of hydrogen atom. And then finally it was upon Wilson and Sommerfeld who gave a set of quantization rules. gave a set of quantization rules back in 1916, where they said that any physical system for which the coordinates are periodic functions of time, uh, these rules must be followed, and popularly they are called as Wilson-Sommerfeld quantization rules. Uh, there were and Planck's and Bohr's quantization were just special cases of these rules. The rules being that the first one being that for any physical quantity or any physical system, let me just write that for you. For any physical system uh, which the coordinates are a periodic function of time, there exists a quantum condition for each coordinate, and that condition being the integral of the closed integral of the momentum multiplied to the coordinate, given coordinate, uh, that is equal to some integral value multiplied with the Planck's constant, where qi is simply the coordinate, and pi is its um, corresponding momentum coordinate, or corresponding momentum simply for that given coordinate. So in case of angular case, we have the angle in place of dq, and we have the angular momentum in case instead of p instead of pi there. So let us just consider or check the derivation of Planck's quantization of energy, and we'll be applying the Wilson-Sommerfeld conditions to a one-dimensional simple harmonic oscillator. Now, for a one-dimensional simple harmonic oscillator, what we get is that the total energy is simply equal to the sum of the potential and the kinetic energy, which is equal to half kx squared plus half uh, px there being the momentum as along the x direction, considered along the x direction, so that is uh, half of p squared divided by m. And if we just take the k, or half of k, as common, and we keep the energy over here, so this is 1 by half of k. I'm writing it like this. I'll be simplifying it for you later. And then we have the px square over here, and that divided by uh, half of m. Well, the k, yes, the k is there, so this is half, and the m as it is lies over here, so m by 2, right? And on the left hand side, what we do is we divide the by itself, so this goes to 1, and so that means this entire equation is divided by the total energy, so the left hand side goes to 1, and here on the right hand side we have x square, and the 2 can go up over here, and so we have 2, and e was divided, 2e by k in the denominator of the first term, and we have px squared divided by uh, again we have, sorry, this is half, so again this 2 can go up, so 2me. So this, if you observe it closely, is a relation which is somewhat in the form of an ellipse, where we have, for an ellipse, we have the formula as x squared by a squared plus y squared by b squared is equal to 1 for a unit radius. And this is exactly the same, whereas in case of a square we have 2e by k. A, that means the a, which is the major axis, we have the value to be equal to 2e by k under root, and we have the value of b to be equal to root over of 2me, because b square is equal to that. And from that what we get is this is the ellipse that we can take it over here, and more or less like an ellipse, right? And this is the value of b, this is the value of a, and this is the origin, this is the x-axis, and instead of y we have the px axis, right? So this is the momentum and coordinate space, or coordinate momentum space, you can say whatever you like. Now the area of this ellipse, if you see, it's simply obtained like this, that is integration over that entire circumference that we have over here, that is px times of dx, and that must be equal to the area of the ellipse, that is equal to pi ab, if you remember the area of an ellipse. And well, the frequency of a linear harmonic, simple harmonic oscillator is equal to, let us say, nu, and that is equal to 1 by 2 pi times root over of k by m, where k is this, exactly this constant, that is the force constant in this case, that is being used. And so what we get is, now here for pi ab we have the value to be equal to, instead of we keep the pi over there as it is, right? So we have pi, and instead of a we have the value root over of 2e by k, and instead of b we can have the value of 2me. Now the e's get multiplied, so we have this to be equal to pi. The 2's get multiplied, so we have 2 pi. We have e, and we have root over of m by k. And if you look at this is just the reverse of it, means the reciprocal, that is 2 pi root over of m by k instead of k by m. So that means we have this to be equal to e divided by that frequency, right? We have this to be equal to e divided by that frequency. Now with this value available to us, what we get is the, let me just write it over here for you before going over to the next page. We'll use this space. Now as per Wilson-Sommerfeld quantization rule, we had a px times of dx integrated over that closed interval to be equal to nh, where n is an integer. And here at the bottom of the page, if you see this here, px dx integrated over the closed loop is equal to the area of that ellipse, and that area enclosed is equal to e by nu. So that means this thing over here is e by nu, and that is equal to nh, and this implies that e equals n times of h nu, which is exactly what I discussed. Let me just take that line for you over here like this, right? So this is exactly the relation which we were looking up to, which tells us that this quantization rule that we are using is pretty much valid. So from this, what we get is, let me take it to the next page for you. We can have a diagram for the allowed energy states of this from this quantization rule that we obtain and the ellipsoidal area that we obtained. So we have this elliptical area, and it has an origin. It has the y-axis to be the momentum and the x-axis to be the coordinate axis. Here it is the coordinate in terms of the general coordinate, that is the Cartesian coordinate system. And here in every spacing of h, remember, this is 1h, this is 2h, this is then it will be 3h. So because it is quantized, so the integral values go on adding up, and these are the allowed energy states that I'm shading, and they are in gaps of h. So this is how the allowed energy states of the oscillators are placed, right? So if we have achieved this for Planck's rule, Planck's quantization, remember we also mentioned about Bohr's quantization of angular momentum. So using Wilson-Sommerfeld rule, let's check for Bohr's angular momentum. Now, in this case, let us take the plane polar coordinates, that is r and theta, and which are periodic functions of time in this case, of course. And the momentum thus associated is simply the linear momentum with the radial component, that is PR is equal to m dr by dt, while that associated with the angular case is p theta, which is equal to the moment of inertia times of the angular speed or angular frequency, so as to say, that is mr squared d theta divided by dt. And these are constants, right? Because the angular the moment of inertia for a given radius is constant, the mass is constant, the rate at which it rotates around the electron rotates around the nucleus, that is also constant as well. So now PR obviously goes to 0 in this case, because R is constant, as you know, so that cannot be considered. So we'll be using this P theta instead. So now, as per Wilson-Sommerfeld rule, we have P theta times of d theta, that's the angle that is swept through, is equal to n times of h, and well, p theta is constant, of course, because we have just mentioned it over here. We have because the rate of angular speed, the rate at which the angle is swept, that is also constant, but the angle thus swept on the whole is goes to 2 pi. So p theta is equal to p theta times of 2 pi is equal to nh, and that just gives me nh by 2 pi, and p theta, as you know, is the angular momentum, that is simply L vector in general uh, designation that we have. So this is the Bohr's quantization law, which is again obtained from Wilson-Sommerfeld set of rules. And so everything falls in place when we are using the Wilson-Sommerfeld quantization rule, which is a very important tool in terms of studying the phase, the momentum space coordinates considered, and the phase that is considered. So that is important from that point of view. we'll be dealing with more such things up next in the next video. Probably we'll be discussing about the Bose correspondence principle, and then we'll be moving ahead further with the topic. But till then, thank you for watching. Do try some of the new miracles that you, if you may, related to such topics that you come across in this channel. And if possible, you can mail me for the answers. We'll try it together. Thank you.